Okay, so now I want to show you Rust in all its glory, and it's here on the malware analysis page. I think it's on the exploit development page too, but anyway, we put it on the malware analysis page yesterday. So you need a Linux machine. It can run on ARM or Intel. It doesn't matter because Rust is a higher level language. And the main one I want to show you here is this one here, basics, overflow, and injections. So here's my SSH connection to my Windows machine, and let me make it big. All right. So we can play some games with Rust. And the first thing is a Hello World app. Um, if you look in here and just look at the code, whoa, that's the executable code. That's not what I wanted. I wanted the source code. L cat he .rs. There we are. So this is the source code, and that's a little screwy. It's printing this weird character instead of yeah, this is supposed to be curly braces, and somehow they're coming out wrong. This probably means, I think I've seen this before. If you hit a funny control character, your terminal turns into some weird mode. So I need to just close it and open a new terminal. Happens with copy and paste too. If you hit a weird character, your copy and paste starts doing weird, stupid things. Let's see if I can go to Rust and then cat um, hello.rs. Yep, now it looks right. That was some kind of weird issue with the terminal. I see it happen all the time. I don't thoroughly understand it. But anyway, the point is to show you that Rust is not very complicated. It looks a lot like C. It's a little bit different. You have this strange bit of the exclamation point here. But anyway, that's the command line. That's the hello world, and I can run it by going into that. Let's see, is it this folder? I think it's hello. I think it's not here. It's in that folder. Um, there. There you go. That runs it, and Rust says hello. So shows you have um, just that Rust is working. And the instructions are here how to install it. You just install a Rust compiler, which goes on Linux machine. Um, and people say in the news I'm listening to, Rust now runs faster than C. So let's see why people love Rust. Take a look at an integer data type, which is int, and then int.rs. All right. So here's one where I define some variables. Let I equals 1, let j, unsigned 32-bit, equal -5, and then print them out. And if you try to compile that, let me just go in there, it'll be easier. Again, I can do Rust C to compile the int.rs, and it won't let me compile it because this is an unsigned 32-bit integer, so it can't be -5. And that's why I say this is the point of Rust. In Rust, you can you can have a default here, which I'm not sure, I don't remember what it is. I think it might be signed 32-bit, but you can also specify exactly what type of data goes in each variable, and then it will warn you when anything bad happens, which is much friendlier to the developer. Instead of just giving you the wrong answer and driving you nuts, Rust will give you an error message as soon as you do something that you really shouldn't be doing. So let's take a look at the adding app. All right, first look at the source code, which is here. So this is going to let a equals 1, and then a equals a plus 1, and then print a. Nothing very exciting. And yet this is also wrong because by default, variables are immutable. You can put data in them, but it will never change. So it warns you, you cannot assign twice to an immutable variable. And this might seem like wasting your time, but it emphatically is not. Carefully defining what all your variables do and then enforcing that and warning you when you do anything strange with them is a lot of the security of Rust, how it avoids serious errors like in C, like this one. If I look at this program, this is a C program. So what I do is I define unsigned character X, and then I put 230 in it. Now, already, this is garbage. I got used to doing this from years of C programming, but this is terrible. I defined a character variable, and then I set it equal to a number. Now, that doesn't really make any sense. Now, I was used to this in C, that a character is an 8-bit integer, and it can carry only variables from 0 to 2, values from 0 to 255, but it all makes no sense because we were thinking in the world of ASCII, and ASCII only goes up to 127. So why do you allow these illegal numbers like 230 in there? And why would you put a number in a character variable anyway? In a proper modern language like Go or Python, a character is a printable character, and that's a Unicode character that can take up to 4 bytes because characters include European characters and umlauts and Arabic and Chinese and Japanese letters. There's a lot more than 127 of them. So this is actually not what a character variable should be at all. What this is an 8-bit integer. But the two are the same in C, which is one thing that's a problem. But the next thing gets even worse. So now I make a loop 10 times, and I add to that variable and print the output. So if I run that, it adds up to 255, and then it rolls around like an odometer and gives me stupid numbers like 2, 10, and 19. It just rolled over, so when I added something to it, it got smaller, and it didn't complain at all. It just runs, assuming that as a developer, I'm intimately aware of exactly the binary representation of everything, and I must have intended that. Which, of course, is the way the developers of C thought, because C was only a small step from assembly language, and they assumed that all the coders know exactly what's going on with all the bits, and they want to do direct bit manipulation. But modern coders don't think that way, and as far as I can tell, they never did. They think at a higher level, and when they have an integer and they add to it, they expect it to get bigger, and they don't anticipate this. So that is the integer overflow, one of the main flaws you see in C. So let's see what happens if you do that in Rust. I've got source code here. So here I do just the same thing in Rust. I make a mutable, unsigned 8-bit integer, and I put in 230, and then I just try adding to it a bunch of times. And if you run that, it will add up to 255, and then it will crash and tell you attempt to add with overflow. It will not roll over and give you the wrong answer and just keep running so you can ship it to production and create a security disaster. It will complain as soon as you try to exceed the rules of what an unsigned 8-bit integer is. This is much friendlier to the developer. You actually learn about your problems and fix them instead of having security disasters caused by them. So now let's take a look at the most famous one, the string overflow. Tried to get this. There we are. So cat str.c. Okay, here it is in C. I define two strings, each long enough to have 4 characters and a null byte at the end, containing A and B. Then I show the addresses where they're stored and the values in them. Then I input a new value for one of the strings and print them again. So if you run this, okay, string 1 contains A's, string 2 contains B's. Notice string 1 is stored at address 48, and string 2 is stored at address 40. So that means if I put in a new value for string 2, that's 4 characters of C, everything works fine. String 2 changes, and string 1 doesn't change. But if I run it again and I put in a longer entry for string 2, then string 2 gets the longer entry, and string 1 changes into some portion of the longer entry. This is insane, and this is because it did not change these storage addresses. It's still storing this one at 58 and this one at 50. So when this one gets longer than 8 bytes, it just overrides this one. And because C has this convention of putting a null byte at the end, now it overwrites the contents of string 1. So this is something that will drive your developer insane. How are they supposed to know that when I get a new value for string 2, it's going to change the value of string 1? How are they supposed to understand that, remember that, and program taking that into account? In practice, they cannot, and we have all the buffer overflows causing huge amounts of problems. And this, again, is something that will not happen in Rust. If we take a look at the Rust version of this and look at the source code, the source, whoops, did it again, clear. Um, I want to print the source code, which is this. All right. So the source code looks very much the same, mutable strings that start 4 characters long. Then you just print the address, enter a new value, and print them out again. But if you run this one, all right, I can put in a new value for string 1, which is the one that's stored earlier. This one is at 2F0 and string 2 is at 308. So string 1 is the one earlier in memory that you might expect to have this problem. So when I add more data, it adds it to the end of string 1, which is a little different than C, but not bad. And now, even if I add a whole lot of extra data, it doesn't do anything bad. I added extra data to string 1. String 1 became longer. String 2 did not change. There was no overflow, no crash. And notice the addresses are still the same. This one is at 890 and that one's at 8A8. That's because if you look in a debugger, you'll see it uses double pointers. What's stored here is not the literal contents of the string, it's a pointer to the string. And when you make the string longer, it readjusts the storage location to some place where there's enough room and changes it. So the strings don't move, but those are pointers and the pointers change. So like any modern language, it automatically readjusts the storage to handle the increased size of the string that's going in there, and it doesn't have a buffer overflow. So that's much superior. Now you can still have flaws. For example, command injection, which we were talking about in the last bit. If you go here, this is CMDI, okay? All right, so here's a program that will read data from the user and then take ping minus C1 and add the data from the user and execute it on the system. So that has a trivial command injection. And so if I put in an IP address like 1111, it does a ping. But if I put in 1.1.1.1 semicolon ls, it does that and then it executes an ls. So I have arbitrary command injection in C of the type we've been exploiting. Now you can do this in Rust. If I go into it's command, yep, go into CMD injection directory. All right, here we are, and this uses a Rust library manager called Cargo, and so you run it. Let me see if I can find my source code. Okay, here's my source code. It's cat src and then main. All right, here's the source code for this, where I again here's the run command ping minus C1 and then insert the variable IP that I read from the user. So this does exactly the same thing in Rust. It executes a command line command with data that came from the user, and therefore it reproduces this problem. You run this thing with cargo run, and now it asks for an IP address. If I give it 1, it does a ping. But if I give it 1.1.1.1 semicolon ls, it executes the ls. So you Rust does not solve all security problems. You can write code that uses input for a command and it won't warn you. Now there are vulnerability scanners like Acunetics, or maybe I think it's Acunetics. Anyway, there are vulnerability scanners that will find this, but the language itself will not save you. So it doesn't solve every problem. All right. Anyway, that's the main thing I wanted to show you. There is another Rust thing here to show you a few fancy things like dangling pointers and memory leaks and heap overflows. You can set these up, and it turns out that Rust stops these too. Now, a lot of these things like dangling pointers are caused by, in C, you allocate heap memory with alloc, and every time you do that, you are required to free it with free. But as you have a complicated program, you might allocate it in one method and free it in another, and end up calling that method twice. So you might have double free, which causes a security vulnerability, or you might fail to free it. So it ends up to being a dangling pointer, and you can read or write to some pointer that points to memory that's not supposed to be in use anymore and contains something important. And those are important vulnerabilities, again, caused by C. And Rust solves this in a brilliant way. What happens in Rust You can allocate memory. You do it with this box command. You can allocate space on the heap, but you don't have separate allocate and free commands. Instead, it's incredibly simple. Anytime you allocate memory on the heap, it notices the current scope, which is the curly brace container you're in. And when you exit that container, it automatically frees it. It is not the programmer's responsibility to remember what they've allocated and free it. It just happens automatically. Anything you allocate survives as long as it's in scope, and as soon as it's out of scope, it's automatically freed. Therefore, you never have forgetting to free it or double freeing it in a very simple, elegant way. So it solves the dangling pointers, and you can examine it in the debugger to see how it works, um, and see that none of these things will happen with Rust. So that's what I wanted to show you. Let me stop this one.